You've most likely heard the statement, some infinities are bigger than others, but odds are you're one of the many people who have interpreted it wrong, thinking that it just means more crowded or dense. In this video, I will go over why and how we can show there are the same number of fractions as natural numbers. First, we need to talk about what it means to be the same size. Let's say we have a set which contains 1, 2, 3, 4, and 5. We know its size, or cardinality, which is 5. But what if we have another set, which we don't have the cardinality of? Let's say triangle, square, pentagon, hexagon, and heptagon. We can show they are the same size by matching every element in set A with a single element in set B. This is called a bijection. If we try that, we can match them like this. Since every element maps to another element and there are no leftovers, it means they are the same size. So now, what if we have two infinite sets, the even numbers 2, 4, 6, 8, and so on, and the natural numbers 1, 2, 3, 4, and so on? To show they are the same size, we have to match every element in each set with 1 in the other, and have no leftovers. So let's see, if we match 1 with 2, then 2 with 4, and 3 with 6, we have effectively matched every natural number with twice its value. As we move up through all the numbers, there is never a point where we run out of even numbers, so we can choose any natural number and get its single even number, or vice versa. So in the end, if you think of any natural number, there will also be a paired even number, meaning there is the same number of even numbers and natural numbers. So what happens now if we want to compare the rational numbers with the natural numbers? Well, firstly, we want to bring some order to the rationals, instead of just having them all mixed up. So let's write them in an infinite table. On the x-axis we have the denominator's value, and on the y-axis we have the numerator's value. Like this, we can guarantee we have every non-zero positive rational number in this table, including all non-simplified fractions. But we need a list, not a table. So what do we do now? Well, if we look at the diagonal, we can create a list. We choose diagonals as they are finite, so we can always move on to the next one. If we chose rows, or columns, we would never leave the first row or column, so diagonals ensure we reach every positive rational. Our first element is 1 over 1. Then we move to the next diagonal, which is this one, which gives us 1 over 2, and 2 over 1. Then this diagonal, 1 over 3, 2 over 2, and 3 over 1. We do this for all the diagonals until we have a full list like this: 1 over 1, 1 over 2, 2 over 1, 1 over 3, 2 over 2, 3 over 1, and so on. Now we can simplify all the fractions and remove the duplicates, as they are just another way of writing the same number, giving us 1, 1 over 2, 2, 1 over 3, 3, 1 over 4, 2 over 3, 3 over 2, 4, and so on. Now all we have to do is add the negatives and 0. We can place 0 at the start, giving us this, and now for the negatives. What we can do is when we see its positive counterpart, let's say 1 over 2, we put minus 1 over 2 as the next element, giving us this. Now all we have to do is match every natural number with a rational number. If we go along this list and assign each rational the natural number which corresponds to its place order, we match 0 with 1, 1 with 2, minus 1 with 3, and so on. This matching is a bijection, so the rationals and the natural numbers have the same cardinality. So now you have a better understanding of what isn't meant by some infinities are bigger than others. An example of such bigger infinities would be the real numbers. If you enjoyed this video, please like, comment, and subscribe. I hope you learned something new, and have a nice day.